Hi, so this is our assignment 4. It's about uh, user password key authentication. So here what we have is a bunch of user password key value pairs, and yeah, the job is to authenticate a user and a password so that you can log in and access a resource, whether it be some sort of a web resource, etc., etc. So we have some Javadoc for this. You can see it online. And you can access, all of these classes and stuff like that. So that's the data in the Javadoc. Then we hit our source folder. So this is entry.java. You can think of an entry as a bucket. Well, obviously, when you have a hash table, you need a hash code to decide which bucket you're going to put your key in. So this is the initial hash code. It's not very good because it can have positive and negative values. This can lead to clustering and degraded performance over time due to stuff like clustering, where stuff like linear probing might not work as efficiently to avoid collisions. Now, a hash table makes use of some components of entry, and it's based on the interface iHash table. It just has a couple of methods. Our custom hash table implementation makes use of linked lists to solve the issue of collisions. This is a pretty fine solution if you have a small sample set, but as the sample set grows, the linked list becomes more and more costly to maintain, and it's not an ideal solution. Also, our output method, it's a bit lacking. Doesn't deal well with duplicates. Resize works somewhat, but it's heavily reliant on the load factor, so you have to get the load factor right. So it's not too ideal, but it does work. Then we have the improved hash table, which is something we scouted from the web and heavily altered to fit with our actual hash table that we implemented. But this is an improved version. The reason this is well improved is if we look at the hash is always positive values, so we avoid clustering. Our resize method is better, and that is because it offers more dynamic ability to resize as needed. If collisions can be avoided using collision avoidance, and the bucket length can be doubled, we can actually have multiple keys within the same bucket, and yeah, this is collision avoidance. When the data set is larger, rehashing would be more efficient than the linked list hash table way of collision avoidance. So this would be more ideal for a larger data set. There are also a few other key performance enhancements comparatively. We have our test class, which does full test coverage of our custom hash table. This one is more so from the internet and edited to suit our needs. But everything in software engineering is somewhat a copy of a copy. Now we hit our main method. It makes use of the data set that we were going on about. I'm just putting in my full path because, well, I still haven't figured out how to use relative path. So we add in a known user and a known password, so something that we know is going to be present in the data set. We measure the performance of each of our hash tables / hash maps, so we'll just call them maps. And we measure all of their performance when a user is present and when a user is not present within a key value mapping. So a login, username, and password in this example. So our different data structures are the inbuilt Java hash table, the inbuilt Java hash map, our custom Java hash table that we made, and our improved hash table scoured and crafted from the web. Now, the inbuilt hash table, it uses a vector-based solution. It's pretty old, and it's not ideal. Even in cases where you want synchronization, a synchronized hash map would perform better. It uses a more modern array-based implementation. So it's just overall better in virtually all cases. You might find a very rare example, probably something with backwards compatibility where a hash table might be better. Then we have our custom hash table and the improved hash table. For some of the aforementioned reasons, the improved hash table performs better. So we can edit the data size here. Now, the reason this is the max number is that's the max number of rows, and we're just setting a limit on that at the moment. So look, if you run this now, this is all in nano time because these things work pretty fast using lookup times, and well, for a hash map, the lookup time is just over 1. It doesn't really matter what the data size is. That's because we're using a hash code to access a bucket, and no matter how many buckets you have, the way you get to that bucket using that hash function is going to be the same amount of time of 1. So we can see as we increase our data set, wouldn't have any effect on the hash map for a known user. Of course, you'll have slight irregularities just by chance. Now, the hash table is synchronized, so it can't run as fast. So the hash map wins in all circumstances. Then we have our custom hash table. It's beat quite soundly by the improved hash table, but if we make the sample set rather small, the overhead of a linked list is tiny now, and now we can sometimes, if we're lucky, find a case where the custom hash table can outperform, but even so, it's unlikely. Now, so what this is doing is it's testing two things. It's testing when the user is present and when the user is not present, and the time for lookup of those two cases. So we also have a graph here for that. What you'll see is that, yeah, the hash map wins in all circumstances. No matter how big the data size is, it's virtually the same amount of time to look something up. The linked list implementation performs better at lower data sizes, and then it becomes more costly as the data size increases. And then rehashing becomes a more interesting approach to take instead of using a linked list. And of course, the hash table is pretty bad. It uses a vector based implementation and it's synchronized, so you'll be hard fetched to find a good use case of that. Yeah, so that's it for our assignment 4.